Okay, let's recall what we did last time. Okay, last time we talked about alternating series. Now, alternating series actually is a series that has actually special symmetry, i.e., its terms alternate its signs. It's plus minus alternating. Then for this alternating series, we have actually some special property because they are actually special. Its convergence is actually easy to determine for alternating series. We give out one example of alternating series, which is alternating sum of the reciprocal of integers. We find it's last time we actually know the even terms of its partial sum is actually increasing. We actually, what we did is we pair the terms such that actually every two terms is positive. Because here we use the fact that it's actually decreasing. 1/4 is less than is greater than a quarter. 1 is greater than half. So we pair them, okay, so that actually it's increasing. We know it's increasing. The partial sum is increasing. Now, actually, another property that we know is actually it's bounded by 1. We pair it in another form. It's 1 subtract positive term, so that we can conclude that it's actually bounded by 1. So we know this partial sum is actually bounded and monotonic. It's increasing, bounded and increasing. Then we know it's actually the series converges. Okay, the series converges. Now, next question is, what does it converge to? What number it converges to? Okay. So we know it converts to some number. Suppose let this number be s. Suppose it converts to s. Now, remember, we only did show that this partial sum, the even term partial sum converts to s. Now you ask, what happens to all the partial sum? Now, all the partial sum, for instance, all the partial sum, s to n plus 1, it differs from s to n by a term. Okay, by a term. So all the power, remember, all the power is the series is 1 minus a half plus a third minus a quarter. So even terms, they are positive. All terms, the even terms are negative. All terms are positive. Even terms are negative. So this should be plus the odd term 2n plus 1. So this will be s to n plus, so 1 over 2n plus 1. You see, if we take limit n approaches infinity, s to n plus 1, this should be limit n approaches infinity, s to n plus limit n approaches infinity, 1 over 2n plus 1. So this will be s plus 0. So this shows actually the even partial sum, all partial sums, they converge to the same. Okay, they converge to the same. Okay, they converge to the same limit. So we actually know limit of the partial sum, even or odd, actually converts to s. Now to summarize, now what this number s is, we will answer this question in a moment. Now, actually, we generalize this. Let's check what we did, what kind of properties that we used to conclude that the series is actually, the series converges. So this tells us the alternating series, the given alternating series actually converge in this. The given alternating series converges. Now to summarize, the properties that we used is the following. First property of the series 1, it's alternating. Okay, alternating. The sign is actually plus minus, etc., etc. Okay, and then the second property is the terms 1/2, 1/3, a quarter, 1/5 is actually decreasing, and this property, from this equation, let's use equation 1. From equation 1, when we take a limit of even term and odd term, we actually see the difference actually approaches 0. So actually we know that the fact 1/n approaches 0. Okay, we use this fact. Now to summarize this kind of properties that we used to abstract, so actually we have alternating series test. The alternating series test says the following. Why? If the alternating series satisfies, suppose we have an alternating series says, if the alternating series -1 to the power n, bn, n from 1 to infinity, this will be b1 minus b2 plus b3 minus b4 plus b5, etc., etc. Such that all the terms bn is positive, satisfies y. It's decreasing. bn plus 1 should be less than or equal to bn. It's decreasing. Two, the limit is 0. Okay, the limit is 0. Then actually we can conclude, then the series converges. Okay, converges. Let's see some example. Let's see the example. N from 1 to infinity, -1 to the power n. So this -1 to the power n is alternating factor over ln n plus 4. Okay. Now this -1 to the power n is alternating factor. So first we check it's alternating. It's very easy to check it's alternating because the reason is -1 to some power n. This is alternating factor. Now the fraction, the denominator of the fraction ln n plus 4 is always positive. Okay, so here bn plus 1. So this will be ln. So here bn is, the positive thing. Is n plus 1 plus 4, so it's n plus 5. bn is 1 over ln n plus 4. So you see ln is increasing. So if our input n is large, then ln value is large. Then the denominator is large. Larger denominator means small fraction. So this actually we know bn plus 1 is less than or equal to bn. So actually we know it's decreasing. So it's decreasing. So we check it's decreasing. So this we know it's decreasing. So the positive terms, the magnitude of terms, they are decreasing. So bn plus 1 is less than bn, decreasing. Then we check limit of this bn. Limit of bn is limit n approaches infinity 1 over ln n plus 1, n plus 4. Now as n approaches infinity, ln n approaches infinity. So this is 1 over absolute large number. So this is actually 0. So actually we check. So alternating series test applies. So we can conclude by the series converges. Converges by the alternating series test. Alternating series test. Okay, example.
Professor, do we have quiz today?
We will have no quiz today. If we have quiz, right now the thing is it's very hard to organize a quiz, on class quiz, because because we are using online class. I'm thinking how to give you quiz. Actually, possibly we will use WebAssign. Right now, I have no idea how our test will be. Possibly we will have online test, or I give you, take home test, or I will, increase the percentage of our homework. Okay, website homework. So we will change our syllabus a little bit, in this situation. Okay, any other questions? Okay. Now here, this is also alternating series. Okay, let's see. Here the Bn term is the sine n over pi. So here B1 is sine pi is 0. Sine pi is 0. So we actually can so because the first factor is 0, so we can actually start from 2. Okay. So as we explained earlier, any finite many terms does not change whether it's converged or diverged. Okay, so it does not matter actually. Okay, so B2 is sine pi over 3, which is root 3 over 2. B3 is sine pi over 4, which is root 2 over 2. Now, yeah, what I did. Sorry, what I did. So this should be B3. Sorry, B3 is 3. This should be B4. So confuse myself. B2 is sine pi over 2, which is 1. Okay. So actually, you see, this is actually decreasing, except the first term. So Bn is actually decreasing. It's decreasing from the second term. Decreasing from the second term. Now, of course, it's alternating. It's also the series is alternating. The given series, we check decreasing. So the series, the given series is alternating. Alternating series. Of course, this is because we have the factor -1 to the power n is alternating. And also we take limit. We check the limit of Bn. It's a limit n approaches infinity sine pi over n. Now as n approaches infinity, we get this sine pi over n. This pi over n approaches 0. So this is actually sine 0, which is 0. So actually we know the limit is 0. So we can conclude by alternating series test. Then we can conclude by alternating series test. The given series, the series -1 to the power n sine pi over n converges. Okay. Now let's do another example. Example. Okay. N from maybe 1 to infinity. Here we have alternating factor -1 to the power n. And we have the term Bn, which is square root of n plus 1 minus square root of n. Okay. Now, first of all, Bn is positive. And also we know Bn, so it's alternating. So it's of course alternating. So we know it's alternating. Alternating. We check it's alternating. Of course it's alternating. Bn is positive. Positive. And also we know it's alternating. So we check whether the limit. So now we check whether it's decreasing or not. So we check decreasing. So it's being decreasing or not. Decreasing. So we check, actually, we write in this manner, it will be really clear. So we rationalize, we write it in this manner. So we multiply the conjugate. We multiply this, multiply the conjugate, and then we divide the conjugate. Then this will be, now the numerator, we multiply the numerator. So a minus b, a plus b. So this will be difference of two perfect squares. So we use difference of two perfect squares. Difference of two perfect squares. Then this gives us that this is n plus 1 plus 1 minus n over square root n plus 1 plus square root n. This will be n cancel n. So this is 1 over square root n plus 1 plus square root n. So this actually, one can easily see here, the denominator is increasing as n becomes large, okay? So the denominator is increasing, which means the fraction should be decreasing. This means Bn is decreasing. Bn is decreasing. Decreasing. Because the denominator is increasing. Decreasing. Now, then limit Bn, you see, limit n approaches infinity Bn, which will be limit n approaches infinity 1 over square root n plus 1 plus square root n. The denominator can be arbitrarily large. Denominator can be arbitrarily large. So this limit is actually 0. Then we can conclude by alternating series test. Then the series, we can conclude by alternating series test. Converges. The test that we use is alternating series test, by alternating series test. Okay. Alternating series test is really easy. Once you check it actually satisfies the alternating series test, then you can conclude that the series converge. Okay. Now you need to be careful. When you apply when alternating series test applies, the conclusion is that the series actually converges. Okay. You never get it's never you get this thing. The series diverges by alternating series test. This is of course wrong. Okay. The conclusion is the series converges if alternating series test applies. Okay. Now remember, let's continue the questions that we left, which is the series y minus a half plus a third minus a quarter plus 1 over 5, etc., etc. What is this series actually converges to? Actually, in earlier section, we did this example. Remember, we have the series. Now, what we did is this: x plus x squared plus x cubed. This is a plus etc., etc. This is a y over 1 minus x. Here, x absolute value less than y. What we did is we integrated. Actually, we get this is a sorry, this is the x, y here. What we did, integrate both sides. Then we get x term-wise, x, take antiderivative term-wise. Then we get negative line, integrate both sides, we get this, okay? Now, if you take both sides to be x to be negative 1, x to be negative 1. So here, x is less than absolute value of x is negative, less than 1. However, here something bizarre happens. Actually, you can. It's also true. It's true. Actually, you can take x to be -1. It's true. It's true. This is valid. The above equality equation is also valid when x is -1. X is -1. So actually we get this. We get -1 plus 1/2 minus third plus a quarter minus 1/5, etc., etc. This is actually negative line y minus -1. So we get line of 2. So finally we get this is actually y minus 1/2 plus a third minus a quarter minus 1 plus 1/5 minus 1/6, etc., etc. This actually we get this is actually line 2. And this turns out to be really ineffective way to compute line 2. The series on the left, converges slow, converges really slow, converges very slowly. Slow converges is slowly converges slowly. So actually we have better way to make it a convert. Okay, we talked about earlier. So what we did is this ln y minus x, ln y plus x is x is alternating sum. Etc. etc. Ln y minus x is x is negative x squared, etc. etc. Then what we did is we subtract them. So ln y plus x subtract. Now we use the fact that ln we can make subtraction to be this we get the twice x plus x cubed over 3 plus x power 5. So we get all the powers of x. So this will be ln x 1 plus y minus x equals twice x plus 1/3 x cubed plus x to the 5 over 5, etc., etc., all the powers. Now actually we take x to be 1/3. Then the left side will be 1 plus 1/3. Then 1 plus x, 1 minus x will be 1 plus 1/3, 1 minus 1/3. It's 4 over 3 over 2 over 3, which is 2. So you get ln 2 is actually twice 1/3 plus 1/3 cube over 3 plus 1/3 to the power 5 over 5. Now this actually converts fast. This series converts fast. It's mimic a geometric series. It converts fast. If you compute the first terms, then you get a 2 over 3. The first term you get 2 over 3. The second terms you get actually 2 1/3 plus it's 81. This will be, what is this? 2 times this 27 over 81. So this is 56 over 81. 56 over 81. So actually the second term, just use the second term, it turns out this actually approximation is actually already good enough. If you have more terms, actually it becomes better and better. So this is actually a quicker way to compute ln 2 by hand. Okay, so this section is actually very easy. Okay. Now let's go to next section. Absolute convergence. Absolute convergence. Absolute convergence. And the ratio and root test. Root test. Okay. Definition. Suppose we have a series, given a series an. Now sometimes the terms can have positive or can be negative. And then we consider with sum of the positive terms, sum of the absolute values, consider a series of the absolute values. Which be A1 plus A2 absolute value, etc., etc. Now definition. If the series absolute value converges, then we see that the series an, the series an from 1 to infinity converges absolutely. Converges absolutely. Okay, converges absolutely. Okay, example. Negative 1 to the power n squared, n from 1 to infinity. This series, if we take the absolute value, then what we get is, if we take absolute value, then this will give us 1 over n squared, n from 1 to infinity. And this converges by p-test. Here p is 2, greater than 1. So by p-test, it converges. Actually, we know it converges to pi squared over 6. Now here, the absolute value, if we take absolute value to every terms, then actually we know it converges. Then by definition, then the series, original series, we see it converges absolutely. Okay, converges absolutely. Now, this example, or a non-example. Let's see a non-example. Negative 1 to the power n, maybe n minus 1, n from 1 to infinity. This is the series that we talk about. 1 minus a half plus the third, etc. Minus a quarter. Actually, we know it converges to, the series converges, okay? The series converges. We know it converges to, actually, to log 2. It converges to log 2. Now, if we take absolute value, now the negative alternating factor, negative 1 and positive 1, its absolute value will be simply 1. Okay, this will be 1 over n from 1 to infinity, This will be, you see, this is the harmonic series that diverges. This is the harmonic series. The harmonic series diverges. Okay, diverges. So in this case, the series actually is not absolutely convergent. So we can conclude it's not absolutely convergent. It's not absolutely convergent. Okay, we give a definition. If a series converges but fails to be but not absolutely convergent. Okay, a series is called a series. Let's use a series En. Sum of this En is called convergent, conditionally convergent, conditionally convergent. So conditional convergent. If it converges, if this converges, but fails, but does not converge absolutely, but does not converge absolutely. Okay. Now example. This series converges conditionally. Okay. Okay, you may ask, why do we need to study absolutely convergent this property? Now here is some fact. If for series, it's it's infinite many sums. Now for finding the sum, we can switch the order. Addition is commutative, so we can switch the order as we want. However, for infinite many sum, this will be another story. Infinity has a lot of bizarre properties different from finite thing. Now you may ask, can we switch the order of summation as we want in a series? The answer is no. In general, we cannot switch the order of summation as whatever order of summation that we take. For series, it's really different from finite many terms. Now, so in general, it's not. In general, we cannot. Now you may ask, in which situation is that we can actually switch the order of summation? The answer is, it works in this situation if the series converges absolutely. Then you can switch the order of summation. Okay. So here is one of the motivations that why we study absolutely convergent. If a series converges absolutely, then you can switch the order of a summation as whatever order you want. This does not change the result. However, for conditionally convergent, it will be another story. Okay, it will be another story. Okay. Some relation between convergent and absolutely convergent and convergent. So first of all, converge absolutely implies convergent. This maybe called a theorem. Converge absolutely, absolutely convergent. Absolutely convergent implies convergent. Okay, so it makes sense. It makes sense. Okay, we use the fact theorem proof. Suppose a series En converges absolutely, i.e. the series En absolute value converges. Okay, now we have 0 is less than equal to En plus En absolute value, less than twice En absolute value. Okay, so we know the right side actually So here the series an plus an also value, this series, the sum is actually, the partial sum is increasing because every term is positive. It's, you know, converges. The reason is by looking at its partial sum, because its partial sum is increasing and bounded, because its partial sum is increasing because every term is positive, so its partial sum should increase this, increasing and bounded. The reason why it's bounded, because it's bounded by this sum twice of the value of an, the sum of this thing, okay? And then this twice absolute value of an, the sum from n from 1 to infinity is finite. Because we know converges absolutely, converges, i.e. this is less than infinity. Okay, the sum of the absolute values should be less than infinity, finite. Okay, so this partial sum is bounded. So the partial sum actually converges. And also we know this partial sum also converges. Partial sum it's partial sum for the series. For the series, you know, this series, it's partial sum of this thing. It's also convergent, converges. Now this is the finite. When we deal with finite, then we can switch the order. So then we know this thing, partial sum, the series, the partial sum for this thing. So let's so the partial sum, then this implies the partial sum of the series an actually converges. Because this partial sum is the partial sum of the others. Okay. Now let's use some notation. Let's use Sn to be A1 plus A2 plus En. Capital N, sorry. S prime N to be a partial sum for this. A capital N absolute value. And S second prime, this will be A1 plus A2 value plus etc. plus En. Now the partial sum for the series, for the three series, then actually we know this thing converges because it's a bounded and increasing, and this actually converges. This is because by definition the absolute value of the terms, actually the sum of the absolute value converges by definition, because this converges absolute, this thing converges. This is the equivalent by definition. So actually we know Sn, which is S prime N minus S double prime N, also converges by limit law. Okay, limit of a subtraction is limit of difference is difference of two limits. Okay, so they converges. So this actually shows that the partial sum converges. So this means this thing converges. Partial sum converges, then the series converges. I.e., we showed that converge absolutely implies convergence. Okay. Now some examples. Example. This example. Sine n over n squared. N from 1 to infinity. Now, this series, we can, sine n is, remember, sine n is bounded from 1 to -1. -1. Now, actually, we can have good control. The sign is, the sine n is changing from -1 to 1. We can actually have good control. This actually sine n over n squared is, this is the, we can study this series n from 1 to infinity. If this absolute value converges, then we know the original series converges absolutely. Okay, we look at this series. Now, first of all, we can use comparison sine n over n squared. This is bounded by 1 over n squared. Now the series 1 over n squared is convergent by p-test. Converges by p-test. By p-test. Here p is 2. So converges. So this we can know that is the absolute value, the series, when we take absolute values for every term, then it converges by comparison test. A comparison test. So because it's controlled from above by the series 1 over n squared, and its partial sum is bounded increasing by comparison test. So we know this thing converges absolutely. Sine n over n squared converges absolutely. Converges absolutely. Absolutely. Now, converge absolutely implies it actually converges. So this implies a series converges. 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 Okay, then we are done. Then we are done. Then we are done. Okay. Okay. Now let's talk about the next thing. We see a ratio and a root test. Ratio and a root test. Ratio and a root test. We talk about first ratio test. Ratio test. Ratio test. The ratio test. Remember, to find the closest formula for a series in general can be hard because there are infinitely many summations that are to be done. We can only have a very limited case, such that we can find a closed sum, closed form of a series. And in this situation, usually we have really good symmetry, i.e., either it's a geometric series or p-test. Okay, so we often compare a series, try to compare a series with geometric series or a p-test. Okay, a p-series. Okay, then the ratio test is actually the comparison is considered as comparison with a geometric series. Okay, so the key idea, the idea is suppose we have a series, given a series, we look for the difference, we look for the ratio, find the ratio, absolute value of the ratio. Now, first of all, this series can be positive or negative in terms. So we consider this absolute value, and see if it converges absolutely or not. If it converges absolutely, then it converges. Now, actually, we let L be the ratio of the absolute values. Now, if the series mimic a geometric series, then this is actually really close to a fixed number. L is really close to a fixed number. So if L is this limit in opposite infinity, L is let me L is this limit in upper infinity. The adjacent terms take up the value. Now, if L is less than 1, if L exists less than 1, then the series AN mimic can be viewed more or less is approximately more or less a geometric series. Geometric series of ratio is approximately a geometric series of ratio, common ratio L less than 1. And then the geometric series in this system converges. Then the original thing we can use comparison. With comparison, actually, we can have a good control of the original series, such that we can conclude. Then we can conclude that this AN converges, absolutely converges. Okay. I.e., this converges absolutely. The given series converges absolutely. Now convergent absolutely or absolutely convergent implies converges. Then this implies the given series actually converges, because absolutely convergent implies convergent. Okay, converges. So this is the idea of the ratio test. To summarize, the ratio test says this: if limit AN over AN plus 1 over AN, this limit L less than 1, then the series AN is absolutely convergent. Now, absolutely convergent, of course, implies convergent. Absolutely convergent, which means it's convergent. And then now if limit AN this ratio is L greater than 1, then the series is divergent. Now remember, for divergent, we don't have a version of absolutely divergent or divergent. Okay, we only have absolutely convergent and convergent. For divergent, it's just divergent. Okay, it's divergent. Okay, divergent. And then part three. If the ratio is equal to 1, then it fails. Ratio test fails. Equal to 1. Then the ratio test fails. Then the ratio test fails. Then we should use other information to conclude whether the given theory is convergent or divergent. Okay. Let's see some example. Okay, let's see this example. Let me find some example. Let's do some ratio test. And from 0 to infinity, 10 to the power n over n factorial. Okay, then we try to find, so the general term an is 10 to the power n over n factorial. So we find the ratio of the two adjacent terms. So this is an general term. Now an plus 1. So we increase n by 1. So this will be 10 to the power n plus 1. and then n plus 1 factorial. Okay, then we find their ratio. Okay, let me find the ratio. Now an plus 1 over an. Take the ratio. This will be 10 to the power n plus 1 over n plus 1 factorial over 10 to the power n over n factorial. So this will be, do the algebra, 10 to the power n. So this will be 10 to the power n plus 1 over 10 to the power n factorial over n plus 1 factorial. Now this will actually 10 to the power n plus 1 over 10, so 10 to the n, so we get 10. Now n factorial times over n plus 1 factorial, then we get cancel n factorial, then we get n1 over n plus 1. Okay, so this will be 10 over n plus 1. Okay, and then we find the limit n approaches infinity, an plus 1 over an. So this will be limit n approaches infinity, 10 over n plus 1, which is, as n approaches infinity, the denominator will be approaches infinity. So it will be, the fraction will be approaches 0. So in this situation, 0, the ratio is 0, less than 1. Then by ratio test, then we can conclude, then the series 10 to the power n over n factorial converges absolutely, or just converges absolutely, and from 0 to infinity, from 1 to infinity, it does not big deal. From 0 to infinity. Okay. Okay. Maybe more examples. Example. Let's see this example. N to the power n over 3 to the power 1 plus 3 plus n. Okay, n from 1 to infinity. Okay, so here an is n to the power n over 3 to the power 3 plus 1. Now we find the ratio. An plus 1 is n plus 1 to the power n plus 1. 3 to the power 3n plus 1. Now we take the ratio an plus 1 over an, which will be n plus 1 to the power n plus 1. 3 to the power 3n plus 6. Now divided by an, so we flip. So n to the power n. This we get 3 to the power 1 plus 3n. Okay, so this will be, if you do algebra, so 3 to the power 3n cancel 3n. So this will be 3 to the power 5, 1 over that. And then this you get n plus 1 over n to the power n, multiply n plus 1. This will be 1 plus 1 over n to the power n. N plus 1. Now you see, this is actually approaches infinity. This factor approaches e. This factor approaches infinity. This is actually, so finally this ratio is actually approaches infinity. So we can conclude, then by ratio test. Now the ratio is actually approaches infinity. Ratio test. The given series, the series diverges. N to the power n over 3 to the power 1 plus 3n diverges. Because the ratio actually greater than 1. Okay. Okay, this gives us a ratio test. Okay, ratio test. ratio test. Now we talk about the root test. Root test. Root test. Root test. Okay. This is also comparison with the geometry series. Remember, for geometry series, now idea. If we have a series an subset, given a series, we study this. Consider its absolute value. Now, so that every term is positive. Now, if we know if more or less this series is comparable with geometric series, suppose this an is absolute norm, is comparable with a to the power n minus 1. Now, suppose it's comparable with this, more or less that thing. Then if we take then then we have nth root of this thing, of the value of an, should be comparable with nth root of this a r n minus 1. So which will be here a is fixed, a r fixed. R to the power, Now, as n approaches infinity, then we have nth power of a is actually equals opposite 1. Okay, and r to the power n minus 1 over r. This opposite r to the power 1, which is r. Okay. Now we can use the geometry series. Now we know if r for geometry series. We know it is this thing. We know it's this converges. If absolute value of r less than 1, diverges if r greater or equal than 1. So by this comparison with geometry series, then we know, then we actually get the root test. The root test says this: if it comparable with geometry series, then we actually get nth root of this thing limited. If limit of nth root of this absolute value of an, this thing should be comparable with the common ratio. And opposite infinity, this limit, if L equal to this thing, so let L be this thing. If L less than 1, then we actually know, then we can compare this given series with a geometry series with common ratio less than 1. Then we can conclude that converges, i.e. the given series, i.e. an absolute value, this series converges absolutely. So you can compute the given series by a geometry series. It's not difficult to compute it. Okay, it's not difficult to compute it by a geometry series. So that the geometric series converges, and the given series is actually computed from above by a geometry series, so that it converges. So this is the idea of root test. Now, if L greater than 1, or L does not exist, then the series diverges. If L equal to 1, then the root test fails. Okay. Now, at the boundary, when L equal to 1, something interesting can happen. Okay. So we need to use more information to actually to conclude. Example. This example, n squared plus 1 over 2n squared plus 1 to the power of n, sum n from 1 to infinity. Okay. So when do we use the root test or ratio test? When there's a power, then actually we can actually use root test. Try to use root test, because when we take a root, the root cancels the power. Okay. So here an is n squared plus 1 over 2n squared plus 1 to the power n. Now the nth root of an is actually n squared plus 1 over 2n squared plus 1. Now L, limit of the thing, limit n approaches infinity, nth root of an is limit, take limit n approaches infinity, n squared plus 1 over 2n squared plus 1. Now this is very easy limit. This limit is very easy, so that you can find this actually limit. You can divide or use L'Hopital's rule. L'Hopital's rule, you get a 2n over 4n, n approaches infinity, L'Hopital's rule. Then you get actually just the 1/2. 1/2 is less than 1, less than 1, less than 1. So we can conclude. By root test. By the root test, the series converges. Converges absolutely. And from 1 to infinity. Okay. Let's see this example. More examples. More examples. This example. This example. N squared. N from 1 to infinity. Okay. Okay. Now an is, you see here we have y minus n, y minus y over n to the power n squared. So that's a power. So it makes sense to take a square root. So we use root test. Take a root test. Use root, nth root of an, or absolute value of an is positive. So this will be nth root. You know, nth root is an to the power y over n. So this will be to the power y over n. Now, then this will be 1 over y minus y over n. N squared times y over n. So this will be n. Okay. Now let's find the limit. Limit of the thing is well known. We did this when we started L'Hopital's rule. This limit is well known. This is limit is well known. This is actually, remember this limit. This limit is actually 1 over e. 1 over e. You use L'Hopital's rule. This limit is 1 over e. Now remember 1 over e. E is around 2.718, etc., etc. So it's greater than 1. So this 1 over e is less than 1. This ratio is less than 1. So actually the given series is mimicking, it's more or less like this thing, e to the negative n, n from 1 to infinity. So it's more or less mimic this geometric series that has a common ratio less than 1. So we can conclude that by root test. By the root test, the series converges. The series converges absolutely. Converges absolutely. Converges absolutely. The series Converges absolutely. Converges absolutely, of course, implies converges. Converges absolutely. Then we are done for this series. Okay. More examples. More examples. More examples. Let's see this example. This example. Sum of terms n from 1 to infinity. -1 to this factor n, 2n to the power n multiply n factorial over 5 plus 8, 5 times 8 times 11, etc., times 3n plus 2. Okay. Here, you may decide what rule do we, what test do we use. Here you see we have a lot of multiplications. So we can use quotient, try to cancel multiplication, okay? Use quotient, division to cancel multiplication. So here, then what we consider is ratio test, okay? What we consider is ratio test. If there's a lot of multiplication, then what we usually do is ratio test, okay, ratio test. If we have only powers, then it's reasonable to use root test, okay, it's more reasonable to use root test. So we use ratio test. So the an is this -1 to the power n, 2n to the power n factorial, 5 times 8 times 11, etc., times 3n plus 2. Now we take the ratio, an plus 1 over an. Now take ratio of the value to kill this alternating factor. So this -1 to the power n no longer show up. Okay. So this gives us 2 to the power n factorial. 5 times 8 times 11 times etc., 3n plus 2. Oh, sorry. So this is n plus 1 factorial. Now this 3 times n plus 1 plus 2. Now we divide by an, so we flip the denominator numerator of an. And now numerator becomes denominator. Numerator is 2 to the power n times n factorial. Then 5 times 8 times 11, etc., times 3n plus 2. Okay, now you see what the factor is remaining. 2 to the power n plus 1, cancel 2 to the power n, so we have a factor 2 remaining. N plus 1 factorial, remember, n plus 1 factorial over n factorial is actually n plus 1, the last term. Okay, so this is actually n plus 1. Now we have some other factor remaining. So 5 times 8 times 11, these terms cancel out. Then what is remaining is 3n plus, when n is, that's one extra factor is remaining. Okay, the last factor is remaining. One last factor is remaining. Okay, so you see what finally we check the limit of this ratio, limit n up to infinity, an over an plus 1 over an. So this will be limit n up to infinity, 2n plus 2 over 3n plus 5. So by L'Hopital's rule, we take a derivative. L'Hopital's rule, this we get 3 over 2, okay? Which is less than 1. So we can conclude that by ratio test, the given series converges by the ratio test. by the ratio test. By the ratio test. Then we're done for this problem. Okay, then we're done for this problem. Okay, now the key to do this kind of problem is you should know how to find out what the general term is. AN, okay? Try to find the general term. Then try to find out the ratio of the two adjacent terms, okay? Try to find the ratio of the two adjacent terms. Then use the ratio test or root test, okay? Use ratio or root test. Okay, now more example. Let's see this example. This example, y minus 1 times 3 over 3 factorial plus 1 times 3 times 5 over 5 factorial minus 1 times 3 times 5 times 7 over 7 factorial. Okay. This, what does this be, etc., etc. Find whether this converge or diverge. So the general term, so let's write down the general term, plus the general term. So you see it's alternating. So we have alternating factor -1 to the power n minus 1. Then we have this thing, product of all terms 1, 3, 4, 1, 3, 5, 7. So usually we have a notation. Double factorial, 2n minus 1, double factorial. Double factorial here means the step length is 2. So this is actually double factorial. So it's factorial, double factorial. It doesn't mean factorial, okay? Doesn't mean that. It's double factorial means, so 2n minus 1 double factorial means defined as 1 times 3 times 5, etc., odd, 2n minus 1. Product of odd factors. So the step length is 2 every time we increase by 2 over 2n minus 1 factorial. Okay. So the general terms is an. So we determine whether it converges or diverge. Okay, an. The general term is -1 to the power n minus 1. And then 2n minus 1 double factorial or 2n minus 1 factorial. So we take the ratio an plus 1 over an, absolute value, and then find what you get. Then this alternating factor no longer show up. 2n plus 1 minus 1 factorial over 2n plus 1 minus 1 factorial multiplied by flip the denominator numerator of an. Now actually we have a lot of cancellation. So this we get a 2n minus plus 2 minus 1 plus 1 factorial. This we get a 2n plus 1 factorial. 2n minus 1 factorial, 2n minus 1 double factorial. So if you check, this double factorial cancels double factorial with the remaining factor, the last term, 2n plus 1. Okay. So if you write more terms, so this will be this 2n plus 1 double factorial with 2n minus 1 double factorial. 2n minus 1 factorial over 2n plus 1 factorial. So this will be, the first factor gives us 2n plus 1. The second gives us 1 over 2n times 2n plus 1. Okay, so you see, this will be exactly, did I miss something? Yeah, so this is actually correct. So it's actually 1 over 2n, which approaches 0 as n approaches infinity. So by ratio test, we can conclude that the series converges. By ratio test. The given series converges. Now the question is what number it converges to. Now here, this series seems reasonable. It has some symmetry. Maybe I assign this as extra credit problem. if you can work on the closed form of this series, then I can consider give some extra credit back, extra credit to you. So it's extra credit converts to what? Extra credit. What number converts to what? Converts to what number? Okay. If you can work out the closed formula, then I can give you some extra credit. Okay. Any questions? Okay. All right. Let's just stop here for today. And continue next week. Continue next week.
Do we have a quiz next week?
Next week, for quiz, we will. Right now, I'm considering what kind of quiz we should be. I probably, have give you quiz